Good morning. So today's class we are going to continue with what we were doing from the last class. So I'm just going to quickly recapitulate with the slide what we did in the last class, and we are going to add more on today's class. Right. So let me share my screen for that. So in the last class, we completed this derivation and we understood that the effect of suspension in hard cornering. So that has got look at our bicycle model has got improved, accounting the suspension effect also into our study. So we very good understood, very well understood that the bicycle model is quite a nice, sufficient model for lateral dynamic study. But in real time scenario, to represent your vehicle, particularly in hard cornering, to study its lateral dynamic aspect, we have to consider also the accountability of suspension. That would give a way to look at not only the directional response study of a vehicle, also to lead to stability analysis, not only in yaw plane stability analysis, also the rollover stability of the vehicle and so on. So that is the reason why we accounted the suspension into our study. When you account the suspension into bicycle model, that you are very clear that the total mass of your vehicle is being again considered as discretized mass, unsprung and sprung mass because of the suspension. And in that process, we defined what is roll stiffness of the suspension that can be expressed in terms of vertical stiffness of your suspension. And then the sprung mass rolls about roll center or the roll axis is what we have seen. In that process, we have derived the expression for roll angle during steady state motion, and we have derived something what is called the roll rate, which is defined as the rate of change of roll. It is change of roll as a function of lateral acceleration. It's not as function of time explicitly said. The roll change for the change in lateral acceleration is what defining roll rate. And we have also accounted our tire is not a linear tire model. Also, it's considered to be a non-linear tire model. Hence, the cornering stiffness is expressed in terms of normal load. And that's exactly what is that you would see in the last class we have done through this derivation. And we have ended our study looking at what would be the effect of the consideration of suspension and non-linearity of tire into our understeer gradient. And that's what we could witness here clearly from this. Here from this terms, this term 1 here is what is for an understeer gradient from our nominal tire cornering stiffness, what we have looked at arised from our bicycle model itself. And additionally, you have this term which is due to lateral load transfer. The moment you consider the suspension, the roll is inevitable, and the roll is what is causing lateral load transfer from inside to the outside during the cornering, and that along with the non-linear effect of tire is responsible for contributing this additional term into our understeer gradient. So you see this red color parenthesis, there are two terms outside, you have your lateral acceleration. So additional effect of understeer gradient could be witnessed the moment you are accounting the more realistic vehicle model with the suspension effect as well. And interestingly, in this, there are two terms. The first term you have WF into this by C alpha F square in the second term. So first term is positive, second term is negative. And all these parameters, WF, C alpha F, and the values of delta F is at F, all are positive, B is positive. So always this first term here is going to give an understeer effect in your vehicle. And the second term is again reference to the rear axle, and that is going to give oversteer effect. So the difference is going to be accordingly accounted in this. Right. So that is what is that we concluded in the last class looking at that. And if you refer this to the textbook of your Gillespie, this derivation, you would see that delta F is at F by 2 won't be there. It's only written delta F is at F. But you have to carefully do that. Delta F is at F, there is only for tire they have referred. And here, this delta F is at F is for pair of tire in an axle. So by 2 that comes here. Otherwise, the derivation, the terms all are correct. And you can look at that here clearly. So here your FIF in an axle, see this is the outer wheel, single wheel, and this is an inner single wheel, C alpha F value, right? So C alpha F is depending on this F is at normal on the tire. So here it is an individual tire. So whatever that in our previous derivation we have taken delta F is at F is what is change in normal load. That is delta F is at F not minus delta F is at F I, like that. So this is that to be carefully understood. So if we are taking here the value of change in normal in a single wheel, then should not be divided by 2. But in our derivation right from beginning, this delta F is at F is change in 2 wheels. By 2 is what is per wheel it will come. And that is to be carefully understood. And of course, this WF here appearing is 2 wheels normal load, right? So with that clarity, we just have finished in the last class the effect of lateral load transfer in understeer gradient. I'm going to look at today additionally some of the design aspects, that is one as camber angle. So what would be the effect of camber angle change on understeer gradient is what I'm going to teach you in this particular period. If time permits, I'm going to extend an additional understeer gradient effect change also due to something called the roll steer. What is it? We will look at it, right? That's the content of today's class. So today's lecture is number 29. So lecture number 29 and today's date 20/10/2021. And we are going to look at today's class. What is the effect of understeer, effect of camber change? Change on KUS is what we are going to look at it. So first let us understand what do you mean by a camber. The camber is the inclination of the wheel. See, we have front axle, rear axle, we have 2 wheels in front axle, we have 2 wheels in the rear axle. So if you look at one single wheel, so what is its inclination of the wheel outward from the body of the vehicle is known as camber angle, right? So let me just draw a schematic diagram of vehicle body with this wheel assembly. Look at this is the vehicle body somewhere here. I have its CG location. And this vehicle has got the 2 wheels from this independent suspension. So let me have the wheels appearing here like that. And the outer wheel here on the side. And these are connected. This is schematic representation. Right? So if you look at here, this vehicle now has got these 2 wheels. This wheel inclination to the vehicle body. So generally, if you look at that would be always like this. So I will have my wheel plane axis. So this is what is wheel plane, right? And this is what is wheel plane. So in this wheel plane, if I have my axis inclination outward, so this wheel plane is slightly inclined with respect to this body, because of the suspension design and so on. So that is what is say some angle here, outward angle, some angle here, and that angle is what is your gamma. Subscript B I use it. It's go to the body, which is by design of your vehicle. Gamma B, right? Both the wheels inclination outward with reference to the vehicle body is what is called a camber angle. So this angle is what is called a camber angle. Gamma B is what is a camber angle geometry. So this angle would change because of the roll effect of your vehicle. Because of the roll effect of your vehicle. So now I have drawn this diagram to represent the vehicle go in a straight line. So the angle which you are here appearing camber angle or outward, right? So what is this camber angle is going to do? This camber angle will generate something called a camber thrust. So that camber thrust is what is going to be additive to the cornering force that is developed because of slip angle. So that's what you'll have to understand. So let us just look at what is this camber angle contribution, right? So before that, let me just look at this vehicle model. Going into that, let me just look at this vehicle model. What would happen to this geometry when I go in a corner? When I go in a corner. So for example, see, I'm going to take now the turn to the right. When I do take a turn to the right or left, how it will be if I take a turn to the right, this would be rotating in the other way, right? So let us just draw this configuration. How does it change according to this now? So I'm going to take a left turn. Let us look at this is coming to be on this side on this turn. If it is going to be on this turning, this body will roll in an outer side like this. So that time the geometry would be changing it like this. So the same ground, on this ground, I would have my tire now. Changed something like that, and this side tire with some angle, and then the similar way here you would see that would have changed this way. So it is lean on the other side like this, and your roll center would be somewhere here, and that roll of your vehicle body would take place. So this is your ground, and say somewhere here is the roll center, and this is RC, and this is the CG location of your vehicle. So this body rolls about this roll center. How when I do take a turn like that, and this would roll on this side like that. So the roll effect would be something seen like this. So now there is a roll, right? And the body here, what was there earlier, that would change now. Let me just carefully draw this diagram. So this body, this line. So let me also have this wheel plane line. This is wheel plane line. This is wheel plane line. Now, what was my camber design geometrical camber angle would be something whatever was there. So I use the same color, blue color, for the design geometrical angle. And you see now the vertical of your vehicle. So the wheel plane and the vertical is red line here is now is changed. So let me use mine vertical from the ground is this line. The vertical from the ground is this line, right? So in this now, let me explain you this diagram with this. So you understood what's happening here is that now you look at the inclination of the wheel plane to the vertical is what does we define here as camber angle when it goes straight. Because the vertical line and the body vertical line or this is parallel. The red line here and the body axis, vertical axis is parallel here. But when in a hard turning like that, so this has become outer wheel and this has become inner wheel. Sorry, this is outer and inner. Carefully. Because it's taking a turn like that. So this is inner and this is outer wheel. So the body rolls from inside to outside, and let us now see that it was the body to this would be always. This is changed. So now this angle would have changed now. Something, this is how this orientation. Don't think this shrunk. I'm just scaled down model. You can see like that. And of course, we have this suspension here. So this is all, what does that is the change now. So what is that you have to look at here is that the angle now is, this is the total camber angle now. So the camber angle change is manifested because of the roll now. And you have, this is my total angle gamma and this is total angle gamma. So here this W gamma B is now here gamma B in outer, gamma B outer, and in this side this angle will be gamma B inner. That's the geometrical angle. Additionally, there is an angle. That angle is roll angle. So this angle is now roll phi. This angle is now roll phi. And that how can you look at here by this? So if I have my roll to represent a line through CG and the roll center, and to the vertical, whatever is this is there with respect to this angle is what is roll. And that angle also get now influence your tire wheel. So this roll happens when after you give a steering input. So you go straight and you give a steering input. There is some lag time. Then the sprung mass rolls with respect to an unsprung mass about roll center, and that roll is going to influence the total camber angle of your wheels. So now this camber angle would generate a force called a camber thrust, which is an additive force to the slip force due to slip angle. So that's what if you look at the variation of this camber angle, sorry, Fy, Fyf. So Fy due to camber as a camber angle, if I take, and that variation would be something similar. In this way it would vary. So I would take now here, this is what is camber stiffness of the tire, and I would have my Fy gamma similar like how did I write earlier. I would have that is gamma C gamma times gamma. So this is camber stiffness. And this is camber angle. And the FIF is what is lateral force due to camber. That's called a camber thrust. And this plot is drawn when slip angle is considered 0. When slip angle is the variation of your Fy due to camber angle alone, if you are doing it in a test rig by taking a single wheel, putting it on a rotating drum, and then give a inclination, change the camber, and you measure this. and that is going to give you such plot, and that plot you get your this for a particular normal load in this say 1000 pounds and zero slip angle. If I find out my camber thrust is function of gamma, that variation goes like that, and then the slope through this, like how did you define your slip angle? Same way, dou f y gamma by dou gamma. As gamma tends to zero, whatever you get is C gamma. If you look at when you define the gamma C alpha, same way dou f y alpha by dou alpha, when alpha tends to 0 at gamma 0 is what we define. Similarly, now you have to look at this condition. So like that, you would be able to get what would be the camber thrust that can be possible on a single wheel. And this camber thrust direction would normally act how, if you look at, if your vehicle is lean on which side, the wheel is lean on which side. So this plot, if you look at, if this tire lean, this is the tire, the lean on this side. So this camber thrust would be in this direction. This is lean in this direction, the camber thrust in this direction. If that is so, in this case now, your camber thrust would be in this direction, right? So Fy gamma inner, Fy gamma outer. And what is your force due to slip angle? That force would be acting at this point in this direction, because this is the turn, your turn, this is your front of the vehicle and you are driving the vehicle, and your right you are taking. That is why I was telling this is the turn, right turn with respect to front of your vehicle, and the roll on the leftward direction. So you see in the lateral force to be developed in this direction. That is Fy alpha due to slip angle. Fy alpha. So what is the interesting fact here? I see I have to draw this arrow length is greater than that of this arrow length. Why? Because the camber thrust, though it is getting vectorially additive to the lateral force due to slip angle, which is primarily major lateral force manifested because of tire property and tire road interaction, because of slip angle generation, that is manifested, and that is what is taking care most of requirement of your lateral force for to generate the required centripetal acceleration. But of course, this can get additive to this, and this camber thrust value, if you look at it, would be almost 1/10 of the force that can be developed by the slip angle in the case of a radial tire. So you can have tires of two kinds, biased ply tire and radial ply tire. We'll look at that details all in our tire dynamics when we go. But now you can consider there are two classes of tires, biased ply tire and radial ply tire. The same amount of lateral force that can be developed by 1 degree of slip angle, to develop the bias ply tire camber angle supposed to go as 4 to 6 degrees. If it is happen to be a radial tires, then it requires around 10 degrees. Equivalent of camber is what is can create lateral force that can be created by 1 degree of slip angle. But 10-degree camber angle all are out of the way from the real scenario. So camber angle is very less. That variation can go up to maybe some 3-4 degrees at the max. Originally, the design camber angle gamma B would be some 1 degrees or 1.5 degrees and so on for a passenger car segment, right? So this is what is background of the geometrical understanding of what is camber and how this camber is going to influence your understeer gradient during steady state motion is what we are going to now look at it, right? And of course, this camber influenced by the suspension design. see this linkages design and so on. We are not going more in detail of kinematics of your suspension, looking at it now. So that itself is a separate module. No, it's very involved. That the kinematics of your independent suspension analysis is more complicated than that of solid wheel suspension and so on. But our study is not going to get diverted to that. Rather, we are going to focus on an important aspect. What would be the effect of this camber change? Now the camber has got changed. Gamma B is now changed. How? The total camber now is how much? The total camber is now the roll plus this. So I have this 5 plus gamma B is what is my total camber. All right. That's my total camber force. And let me look at now the derivation for to understand the effect on industrial area. So what is that? How do I go about doing it? Let me write the total lateral force Fy during hard cornering now is given by C alpha into alpha. It's per axle. This axle can be front axle or rear axle. So I take from one axle and C alpha into alpha minus C gamma into gamma. Why this minus? It's an additive vectorial addition, and we have seen that the directions are opposite. So that comes like this. And let us say this is equation 1. And now in this, I want to get what is my slip angle. Ultimately, what is my requirement to look at my fundamental governing equation of steady state motion is given by the requirement of steering angle is from 57.3 L by R. In degrees to right, I have this factor plus alpha F minus alpha R. Here I don't account the direction. I just put the absolute value of the angles here. Right. So this is what is that equation that we have seen. So I have to substitute for alpha F and alpha R. So this is the general total sum of lateral force in axle. I can write now what is the slip angle here. That so this term goes on the other side, and it is going to be Fy plus C gamma into gamma, and the C alpha is brought down, so by C alpha, right? So this is the equation number 2. And we know now in steady state motion what is Fy, that is W u squared by Rg, W squared by Rg. That's equation number 3. Because it's Fy is equal to MRU is only equation in steady state cornering governing equation. So if that is so, now I can write what would be my FYF, front wheel axle total lateral force. That would be the normal load in the front axle times U square by Rg. And FYR would be WRU squared by Rg. Right? So let's say this set of equation is number 4. So if that is so, I can get from this from 2, I can get what would be the slip angle in the front axle wheel. So alpha is going to be. So you can assume that's a bicycle model now. The tires are collapsed and then you have it, one wheel. Alpha would be given by now by substituting this here. I would have. So let me just put in this equation that's going to be Fy by C alpha F. So the C alpha becomes C alpha F plus C gamma subscript F. I use it because the camber from the front axle wheels, camber stiffness by camber cornering stiffness, C alpha F into gamma. So that's the equation gamma F. That's one equation. And similarly, alpha R would be Fyr by C alpha R plus C gamma R by C alpha R into gamma R. So let's call this is equation set 5. So having this equation 4 and 5, and we have understood clearly that your effect of road. So what is happening? Hard cornering, you give a steering input. After you give a steering input, there is a time lag, then the roll of your vehicle takes place, right? As the roll takes place, that is going to contribute to the change in your camber as well. So to account that, I'm just going to define my camber angle given by dou gamma by dou phi into phi. So why is it so? Is because I define here what is called a camber gradient. So this camber gradient is what is the change in my camber due to the roll of my body, vehicle body. Multiply that by the roll angle would be what is the gamma. So this gamma would account your geometrical gamma b value as well as the roll. So the roll plus that comes. So that's what we are seeing. So the change here, this gamma is going to be now with respect to this. Right. So the this and you know now in the previous analysis the role of sprung and roll stiffness and the body roll can be represented. This how can I find this roll of my vehicle? That can be obtained by, so this term as it is. So this phi can be given by roll rate times what is my lateral acceleration, right? So roll rate is given by dou phi by dou ay times lateral acceleration. That's all. So this is equation 6. So how do I look at that? Now the gamma is function of roll. So I have this gradient times gamma, gradient times this phi roll, and roll in turn is given by roll rate into lateral acceleration, which we have seen in the last class. So my gamma camber is come like that in a particular axle. So now I can substitute this into my equation 6. So from equation 4 and 6, the phi equation can be written. So I'm going to substitute them into my equation 5. So the 6 I have and 4. I had to put both of them into this. I would be able to get this following equation. So from 4 and 6, the equation 5 becomes as follows. So what is that? It is going to be alpha f fi f by c alpha f, right? Fi f by c alpha f. So that's fi f by c alpha f plus this. So that term is going to be wf by c alpha f into ay. Why do I write ay? You see, this is ay. U squared by rg is what is ay. So I just substitute in that. So plus c gamma f by c alpha f, and I have to substitute for gamma f, and gamma f I'm putting it in this term. So that's going to be dou gamma f by dou phi into dou phi by dou ay into ay. In the similar way, I can write it. What is the slip angle expression that account the change in camber now? So that's going to be WR by C alpha R into AY plus C gamma R by C alpha R into dou gamma R by dou phi into dou phi by dou AY into AY. So let me call this equation set 7. So now our good fundamental governing equation Roman letter 1 is there here. I'm just going to substitute gamma f and alpha f and alpha r in that. So put 7 in 1. Put 7 in 1. I get delta f equals 57.3 L by R plus, if I substitute this, you see here I have ay term, here I have ay term, I can take it out. So I would have here WF by C alpha F minus WR by C alpha R. That is the term comes from tire compliance. And then now I have this term. So that would be now this. So what is that? The C alpha, C gamma F, C gamma F by C alpha F into dou gamma F by dou phi minus C gamma R by C alpha R into dou gamma R by dou phi. So for these two, I have this common roll rate, dou phi by dou AY. And for this all, I should take out what is outside is AY, A subscript Y, A subscript Y. So this is my equation 8. So in this, you can look at, I have this is term 1, same as that of the understeer gradient that comes from tire compliance with a nominal cornering stiffness value. And this is what is due to camber change. So this is K due to camber change. So this is an addition into our understeer gradient value that has to be noted. So these camber angles are very small, no, in case of a solid axle. So independent suspension, they are very important, cannot be neglected. But if you look at in solid axle suspension, in solid axles, the change is very, very less, 10% or lesser than that of the value of the lateral force that can be developed by the slip angle, right? So the camber changes both this camber change comes both due to body roll as well as normal camber change in during the roll of the axle. So what will happen when you when you take a hard cornering, your vehicle here, this picture, let us look at. The vehicle here, this is the inner and this is the outer. So the inner vehicle is under Johns and outer vehicle is under rebound. And this Johns and Johns and rebound is what is representing that the role of your vehicle body as well as the role of your the change in camber due to Johns and rebound. Both are responsible for this total change in camber, and that when you account, you have your values like that, right? So this is one part of that. So you get added. Now there are three terms that comes. So you may wonder what happened to lateral load transfer here. I'm not accounting the lateral load transfer, the role all. So I can map what we did in the last class along with that, and then I can do. That's what I was telling. The free body diagram is drawn for the requirement of forces only in that context, right? So you have studied in your rigid body mechanics. I have a system of force which are maintaining the dynamic equilibrium. I can divide that system of forces into set of system of forces for the individual dynamic equilibrium as well. Right? A free body diagram can be represented like that. So we just take it for the context and then we are looking at the required forces. So I do not bring in here my roll and roll rate and the moment taking here and here putting normal load and so on. You may wonder where is that weight all. Those terms I'm not drawing it. If I put the same in this diagram or the diagram what I have used in the previous case along with that if I account camber, so I will have all these three terms coming. So for a convenient, we are looking at an individual effect and that makes us to go and understand easily these derivations, right? Yeah. So now let's look at one more effect, something what is called a roll steer effect. Roll steer effect, right? So what is this roll steer? Can anyone answer? What do you mean by this roll steer? how that is coming. See, the camber change, you are able to understand there is a geometry involved, and you are seeing. So the role of your sprung mass due to suspension, we have so far both of them very clear. What is this roll steer that is called? Can anyone? See, when the vehicle is undergoing a hard cornering, you know now as the suspension effect, the body rolls. When the body rolls, that would induce the wheels to steer. That will induce wheels to steer. Of course, you are holding the driver of the vehicle holding the steering, and then he does. So that all effect can be dampened quickly. That effect may not be pronounced also. But if you are imagining, which we should not do it, when you go and you corner and you do not hold your steering control, then there will be an additional effect on your steering. Already the wheels are steered and you get an additional steering angle that comes into your vehicle. That is what is called a roll steer. And that additional steer angle is not given by the driver through the steering wheel. Rather, that is being pronounced in your wheel because of the roll of your vehicle body. So that steering is not an instantly happening. So it has some phase lag from that of the roll. So when you give steering, hard cornering, so the load transfer from inner side to outer side, the body rolls, all we have studied. And as the body rolls started rolling, then you have pronounced steer effect in your wheels. That is what is called the roll steer effect. Roll steer effect. So the roll steer is defined as the steering motion of the front or rear wheels with respect to sprung mass that is due to the rolling motion of the sprung mass. Consequently, what is that is happening? The roll steer effect on handling lacks the steer input, avoiding the roll of the sprung mass to happen. That's what is written in the textbook. So you have to give a steering input and you have to see that the body rolls, and then this roll of the wheel pronounced. So how do you account that to see the influence on the understeer gradient? So for that, let us define a gradient now called roll steer coefficient. So gradient is called roll steer coefficient. I'm going to define a term called a roll steer coefficient. And that's been given by a letter epsilon, small epsilon. And this roll steer coefficient is defined as the degree steer per degree roll. Decrease steer. When I say steer angle, it is at the wheel. Steer wheel angle, it is at the hand of the steer driver. That is steering wheel. And this is wheel steer. So the steer, degree steer per degree roll of the sprung mass. And how can I put that as here this way? So I would define this equal degree steer by degree roll. So it is the dou delta by dou roll into roll angle, right? Into roll angle. So the roll angle that we have defined, roll rate into roll angle. So roll rate is what is dou phi by dou ay into ay, not roll angle, into ay. So this is how I can define my side. Therefore, I can write like the earlier derivation straight away. What is this roll steer effect on K as epsilon F minus epsilon R into ay. So you know now what is the terms here. So epsilon F is here delta F F here by dou phi. Why subscript is not put earlier, it can also be rear wheel steer and so on, right? Dou phi by dou ay. So I would have here in the front axle steer effect and the rear axle steer effect. So though the steering mechanism for the front axle by the driver input, the steer effect can be pronounced because of the roll with some phase lag on the rear axle as well. So then I have to put this as delta F. So here it is dou delta F by dou phi into dou phi by dou ay minus dou delta f, dou delta f, sorry, delta r by dou phi into dou phi by dou ay is what is now my so here itself I should remove this, right? Here itself I should write it like this. Yeah, this AY is not there here. AY should be put here. Like that. When I substitute this here, I have here AY term. AY term. Okay. So this is dou phi by, so dou phi by dou AY. Dou phi by dou AY. Dou phi by dou AY. So now you may question that see here what is that I have? Coefficient is this is like this. So this coefficient, if I substitute, so I get this stuff, and hence this. And this is what is your Rolls-Steer effect. This is what is your Steer gradient change. And this positive Rolls-Steer coefficient, this is, sigma value, this epsilon value can be positive or negative. The positive value of this causes the wheels to steer to the right in a right hand turn. That means what? Right hand roll, not right hand turn, right hand roll. So the positive value of this refers to what? Refers to wheel steer to the right in right hand roll. So right hand side roll would take place when vehicle takes left hand. Left hand side roll will take place when vehicle takes right turn. Right? That means what? It is left turn. The vehicle goes on taking a left turn and the roll is to the right and the epsilon is positive like that. So the other way it is negative when it is rolls to the left in a right hand roll. So if the wheel steer is to the left in a right hand roll, then it is negative, right? Then it is negative. So this would cause this contribution, positive value would be for an understeer effect always. And the negative value of epsilon is for oversteer effect. So negative value of epsilon for oversteer tendency. So what is negative value? Negative value of that again look at refers to the wheel steer to the left in a right hand roll. To the left in a right hand roll, then it is negative, and that would be what is called that effect would be of oversteer effect. So this can be best understood in case of a solid axle suspension wheels, right? So let me just to give you that example here. So let us look at, you would see in a heavy vehicle, trucks and so on, the chassis unit. And in this chassis unit, I have my wheel. So you may assume that whatever I'm drawing is for rear wheel, right? This is the wheel. It is the rear wheel. So just change the diagram. Rear axle. rear axle wheel. And you have something called a trailing arm here. This is the trailing arm. So the inclination of this trailing arm, let us say that's angle beta. Inclination of this trailing arm angle is beta. And the roll center or the roll axis of your solid axle in suspension is an arbitrary. The axle will roll, the axle rolls. So body rolls as well as an axle roll. So axle roll about roll center. Sprung mass also rolls about roll center. Roll center is that point which connects both these masses. So this axle rolls about roll center. That axis of the roll of the axle is an arbitrary and it is always assumed to be with the same inclination as that of this trailing arm or leading arm inclination. So if we consider this angle here, beta, and this arm direction is what is your roll axis, you see there is a roll of your axle. Look at the roll of axle. The roll of axle, now how does it been happening? You have to see. So let me just draw a schematic diagram once again representing your rear part of your vehicle chassis and your axle. This axle is what is rolling. So let me just have with some geometry drawn like that. Right hand I have my wheels. Here is the wheel and here is another wheel. And this is the right axle, connect this wheel. And this axle now has rolled like this, right? So look at now what is that is the roll. So this angle is what is the roll angle, phi. You understand how this roll angle that comes? This angle comes. So what does this I have drawn as the platform of your vehicle rear portion and this is the axle and I have my trailing arm now is here like this. My trailing arm is from here. It's like this. This is my trailing arm and this is my trailing arm here. So you see here what is happening is as this rolls in this direction, the platform rolls in this direction means what? It is inner side and that is outer side and this is rear axle. So what is that I consider is rear axle and this is the inner side and that is outer side. That's why the roll angle in this way it is, right? So now what has happened, this angle beta here is increased here whereas on the outer side it is decreased and in inner side beta increased, outer side beta increased, sorry, decreased, right? The roll axis inclination is equal to that of this beta we have considered and then now the roll takes place and you see there is an increase in beta here, a decrease in beta here, right? So this would make the generation of forces in this way. So what is that way? This wheel will be pulled forward and this wheel will be pushed backward, right? The roll steer effect is such that this axle roll makes this wheel to pull forward, goes this backward. That means what? In the rear axle, solid axle suspension it is. So this is that axle here what we have. And this comes and this goes means what? And the turn is in this direction. Sorry, turn is in this which side? Turn is in inner side like this. Turn is like that. When I turn like that and it goes like this and this is pulled and this is pushed, what will happen? This axle goes out of the turn, out of the turn. So refer to what? Out of the turn refers to what? It is going to contribute to oversteer tendency because already the vehicle goes in this side and this goes like that outer that push the vehicle on an inner side. So the effect would be oversteered effect. Oversteered effect. If the initial orientation of the rear axle of the trailing arm angle, here it's downward and here it is going up, what is happening is making the inner wheel, making the inner wheel pushing forward and outer wheel backward would cause in the rear axle, right? See, imagine our bicycle model or your schematic diagram of the vehicle. So this is my front axle. This is my rear axle, right? If this take a turn like that, and I have here, this is pushed like this and this is pulled like that. So this is in a turn, this is taking place in a turn. This push force and pull force backward is because of this increase in beta here and decrease in beta here. That's what is creating such force, and that makes this rear wheel, this is rear and this is front. The rear wheel goes like that, will push your vehicle inward. So your vehicle goes on the steering side itself, right? Your vehicle, I want to take a turn like that, my vehicle also getting pushed in that direction further. That is what is taking a vehicle to an oversteer effect. We normally do what when your vehicle is taking a turn and you give an increase in steering angle for that. But in spite of giving a steering input, this effect of your roll steer, adding to that steering in the rear wheel, would create an oversteer effect. That's what you have to understand. Right. So how can I bring this oversteer effect into an understeer effect? So that comes from the design of your trailing arm. So you can have three arrangement of trailing arm. So let's look at a wheel in particular. This is the wheel in particular, and I have the rim, and I have here the hub. So schematic diagram just to draw. So there is a schematic diagram of this. So this is the wheel, and my roll center now somewhere here. So this is my roll center. So what is my roll center here? Is having roll axis inclined to this. So the roll center somewhere here, and with respect to roll center, my orientation of this trailing arm. This is what is trailing arm. Trailing arm. So this trailing arm inclination from here is 0 like this. Then that would contribute for neutral steer effect. The one what is appearing here, if I take the trailing arm in this direction, that is obviously going to contribute oversteer tendency in the vehicle. If I have another way, my trailing arm down like this, then it will contribute for an understeer tendency. So coming back to this discussion again, the trailing arm here is downward from this. So it is kind of this orientation on that. So I can also have the trailing arm on my vehicle where I can have an attachment here and then this kind of orientation. If that would have been taken here and we study, this will be in another way effect. So this will be pulled backward and this will be pushed forward because here beta would decrease, inner side and outer side would increase, and the turning would be when a vehicle turn like that, this rotation would be on the other way. So like that it would be, and that would since it's rear axle like that comes and then this should be turning, but this turns in this side, that would push outward, then you have to have more correct. That is what is an understeer effect. So this is what is the reference to inclination of suspension roll axis in solid axle suspension, and the rear wheel only we looked at, and then we are able to discuss on this roll steer effect. So I stop at this point now this lecture, and we will look at in the next class 3 more points additionally, and that completes additional effect on understeer gradient due to design aspects as well as the operating condition or the all accounted, right? With that note, I'll stop, and if you have any doubts, you can. Otherwise, meet again in the next class.